The way that a phase lock loop can be used to measure phase is as follows. You have a signal of interest and you have a local oscillator, noted down the bottom there as a VCO, a voltage controlled oscillator, because that local oscillator can change frequency. What you do is you put those basically into a single phase lock-in amplifier. That mixer and low-pass filter combination is a single phase simple lock-in amplifier. And what happens here is that if the incoming signal and your internal local oscillator are the same frequency, then the phase between them is fixed and nominally zero. As the frequency of one of them changes, the external one changes, phase starts to accumulate between those two. The output of the single phase lock-in amplifier starts to increase. That feeds back, on this path here, feeds back into the voltage controlled oscillator that causes the local oscillator frequency to change to catch up with the input signal. And it'll keep moving towards the input signal until the output of the phase detector of the single phase lock-in amplifier starts to stay steady. So in this way, as the input signal changes, the voltage controlled oscillator frequency also changes, and the two chase each other around. They're locked together. They're locked to the same frequency as each other. That's the locked bit of a phase lock loop. So this is nice because it means that you have an oscillator here from which you can directly read out the frequency of the signal that you're inputting to the system. And if you take all those little frequency deltas, the way that it has to move in order to chase that input signal, if you take all of those and integrate it, add it all up, then you get your measurement of phase. So you can see here, we've got our phase lock loop is this core loop, but if you take this kind of error path, this output from the single phase lock-in amplifier, this phase detector, you integrate it out, that gives you the phase of the input signal relative to the internal oscillator of your device.